The universe is a river, and every galaxy is caught in its current. We are only beginning to chart the hidden cosmic flows revealed by mapping the motion of thousands of galaxies. By the end of this journey, you will see the cosmos not as a static picture, but as a dynamic, evolving dance. What mysterious force tugs entire superclusters in a single direction? And could our entire galactic neighborhood be rushing toward an unseen horizon? This exploration will challenge the laws of physics as we know them and redefine our address in the cosmos. What does it feel like to be a passenger on a current you cannot see? The water you drift upon is not still. It has a direction, a purpose, a current. This is the reality for our galaxy and every other within our vast cosmic neighborhood. We are not simply expanding outward in a uniform, gentle drift from the Big Bang. Instead, we are caught in something far more structured, a river of galaxies, thousands of them, all moving together. Astronomers call this a bulk flow. It is the coherent, sweeping motion of immense volumes of space, as if some immense hand is guiding the course of entire superclusters. To understand the scale, picture not one leaf floating down a stream, but an entire forest of leaves, all carried by the same powerful current. This motion is layered on top of the universe's overall expansion, a hidden pattern within the chaos. For decades, the guiding principle of cosmology was the cosmological principle, the idea that on the largest scales, the universe is smooth and uniform, like a perfectly risen loaf of bread. There should be no preferred direction, no grand current. The discovery of these bulk flows was the first sign that the loaf might have a hidden swirl, a structure woven into its very dough. This organized motion points a gravitational finger toward something monumental. Galaxies move because gravity pulls them. If thousands are all streaming in the same direction, it means there must be something out there with a gravitational pull so fierce it can orchestrate this cosmic symphony. We are not just floating, we are being pulled. The question now is not if the river exists, but what is its source? What colossal, unseen landscape of mass could possibly create such a universal tug? This river of galaxies has a measurable speed. Our own local group of galaxies, including the Milky Way and Andromeda, is racing through the cosmos at a staggering velocity of over 600 kilometers every single second. We are not drifting, we are on a bullet train through the void. For a long time, astronomers could measure this incredible speed but could not see what was pulling us. The answer seemed to lie in a specific patch of sky toward the constellations of Centaurus and Hydra. There, something immense was exerting a gravitational pull on everything in our vicinity. They named it the Great Attractor. Mapping this motion was a detective story written in light. By studying the light from thousands of galaxies, astronomers use a tool called redshift. Think of a siren on an ambulance. As it moves away from you, the sound waves stretch out, lowering the pitch. Light from a galaxy moving away from us does the same thing, its light shifting toward the red end of the spectrum. By carefully measuring this redshift for galaxy after galaxy and comparing it to their estimated distances, scientists can create a three-dimensional map of not just where galaxies are, but how they are moving. The data painted a clear picture. Galaxies on one side of us showed a particular pattern, while those behind us showed another. All the local motion pointed like a compass needle toward that one dense region of space. The Great Attractor became the first major landmark in our understanding of cosmic flows. It was a monumental discovery because it proved a powerful idea. By charting the motion of galaxies, we can literally see the invisible. we can detect the gravitational signature of colossal amounts of mass that our telescopes cannot directly observe because it is either too dim or hidden behind cosmic dust. This hidden mass pulling on everything around it revealed itself only through the shared journey of the galaxies caught in its grip, yet the story was frustratingly incomplete. Our own Milky Way galaxy, with its thick band of stars, gas, and dust, the galactic plane, sits directly between us and the Great Attractor. It is like trying to see a magnificent mountain range through a dense, permanent fog. The very thing we were trying to study was partially obscured by our own celestial backyard. So, was the Great Attractor the final destination, the source of the cosmic river, or was it merely a waypoint, itself pulled by something even greater lying further in the shadows? The Great Attractor was not the end of the line. It was, in fact, just a signpost pointing toward a far more colossal destination. As astronomers refined their maps and extended their gaze deeper into the cosmos, they made a second, even more profound discovery. The river of galaxies we are caught in does not originate at the Great Attractor. That dense region of space is itself in motion, being pulled by something with a gravitational pull of almost unimaginable scale. Our entire local flow is being drawn toward the largest known concentration of galaxies in our observable universe, a place known as the Shapley Supercluster. Think of it as discovering that the strong current in your local bay is not caused by the bay itself, but by the tidal pull of the entire ocean beyond it. The Great Attractor was the bay, Shapley is the ocean. This supercluster is not merely a large group of galaxies, it is a staggering metropolis of matter. It contains tens of thousands of galaxies bound together in a gravitational web so dense and immense that its influence stretches across hundreds of millions of light years. To map its influence, scientists had to look far beyond our immediate neighborhood. They measured the precise motions of galaxies across vast volumes of space, creating a grand chart of cosmic drift. The data revealed a clear pattern. While the Great Attractor pulls on us, the entire complex, including us, the attractor, and countless other groups, is all streaming toward the gravitational well of the Shapley Supercluster. This finding fundamentally reshaped our model of where mass truly resides in our cosmic vicinity. For a long time, we pictured mass as being somewhat evenly distributed. But Shapley revealed a universe of shocking imbalance. A single, titanic structure holds a disproportionate amount of the mass in our entire corner of the cosmos, acting as a cosmic anchor around which everything else slowly pivots. This anchor does not just sit there. Its immense gravity creates a slope in the fabric of spacetime, and galaxies, like marbles on a tilted table, naturally roll in its direction. Our Milky Way's high-speed journey is, in part, our long, slow roll down that cosmic slope toward Shapley's immense domain. So, if this supercluster is the dominant force, the ultimate destination for our galactic river, does that mean we have finally found the source of the current? Or does this, too, point to something even more unsettling lying in the darkness ahead? The real magic lies in separating the universal drift from the local current. To map the hidden flows, astronomers perform a cosmic calculation. Every galaxy has two motions blended into the single redshift we observe. The first is the Hubble flow, the smooth, relentless expansion of space itself that carries galaxies apart like raisins in a rising loaf of bread. This motion is predictable based on a galaxy's distance. The second motion is far more intriguing. It is called a peculiar velocity. This is a galaxy's individual motion, superimposed on the expansion, caused by the gravitational tugs of its massive neighbors. It is the galaxy's own personal journey within the grand river. To see the river, you must subtract the universal expansion from the total motion. Imagine you are on a moving walkway at an airport. Your overall speed is the walkway speed plus your own walking pace. If you want to know just how fast you are walking, you subtract the speed of the walkway. Astronomers do this for hundreds of thousands of galaxies. They use massive surveys like the 2-micron All-Sky Survey, the Sloan Digital Sky Survey, and the 2-degree field galaxy redshift survey. These projects are the cartographers of the cosmos. They do not just take pretty pictures, they meticulously record the precise position, and most importantly, the redshift of galaxy after galaxy after galaxy. This creates a 3-dimensional census of the local universe. With this immense dataset, scientists can calculate the expected Hubble flow velocity for each galaxy based on its distance. They then subtract that predicted expansion speed from the galaxy's actual observed velocity. What remains is the peculiar velocity, the signature of the local gravitational landscape. When you plot all these residual motions, a pattern emerges from the noise. Instead of random jitters, you see coherent streams, thousands of galaxies, each with its own little peculiar velocity, all pointing in similar directions, revealing the vast, sweeping currents beneath them. This residual velocity field is the map of the cosmic river. It shows not where things are, but where they are going. It is a direct readout of gravity's influence across hundreds of millions of light years, allowing us to trace the pull of hidden giants like the Shapley Supercluster. This technical foundation transforms a philosophical wonder into measurable science. We are not just imagining a current, we have charted its flow. But what happens when you follow this map to its logical extreme, tracing the river of galaxies back to its deepest source? The answer leads to a confrontation with one of cosmology's greatest mysteries. Our high-speed journey through the cosmos leaves a permanent mark on the sky. This mark is not written in starlight, but in the ancient afterglow of creation itself, the cosmic microwave background. This faint, uniform glow is the cooled remnant of the Big Bang's first light, bathing the entire universe. It should appear perfectly even in every direction, a final echo of a hot, dense beginning. Yet, when we measure it with exquisite precision, we find a subtle but undeniable pattern. The sky ahead of us, in the direction of our motion toward the Shapley Supercluster, appears ever so slightly warmer. The sky behind us is ever so slightly cooler. This is not a defect in the data. It is a direct consequence of our velocity, a relativistic headwind created by our own motion. Just as the sound of a passing train changes pitch, the light from this primordial glow is shifted by our movement. We are plowing through this sea of ancient photons, blue-shifting them in front of us, making them appear hotter, and red-shifting them behind, making them cooler. Scientists call this pattern the CMB dipole. It is the universe's most precise speedometer for our local group of galaxies. By measuring the temperature difference, we can calculate our exact speed and direction through the fabric of space relative to this primordial rest frame. It tells us we are moving at about 630 kilometers per second. This measurement is stunningly independent. It comes not from looking at galaxies, but from listening to the whisper of the universe's infancy. This creates a powerful and critical test for our entire understanding of cosmic structure. We have two ways to measure our motion. One comes from the ancient light, the CMB dipole. The other comes from mapping the gravitational pulls of all the galaxies and clusters around us, like the Shapley Supercluster. In a perfectly understood universe, these two measurements should tell the same story. They should agree on our speed and point in exactly the same direction. For the most part, they do. The bulk of our motion is indeed explained by the gravitational tug of nearby massive structures. But a subtle, intriguing tension remains. When we subtract the pull of all the mapped matter, our motion relative to the CMB is not perfectly accounted for. There is a residual flow, a slight mismatch in both speed and direction. This discrepancy is a whisper from the darkness. It suggests that our catalogue of cosmic giants, vast as it is, might still be incomplete. Could there be structures even larger than the Shapley Supercluster, so immense and so distant that their light has not yet reached us, but whose gravity is already felt in the motion of galaxies? Or does this hint at something more fundamental, a flaw in our standard model of cosmology itself? This tiny tension between the ancient light and the modern map is where true discovery waits. It is the faint signal that our river of galaxies may be flowing toward a source we have not yet imagined. That faint tension in the data became a roar with a truly unsettling discovery. When astronomers looked not at nearby galaxies, but at the most distant galaxy clusters they could find, they saw something that should not be possible. These clusters, billions of light-years away, appeared to share a common motion with us. This phenomenon was named the dark flow. It was as if the entire observable universe, from our local neighborhood to its farthest visible reaches, was caught in a single, vast current flowing in one specific direction. To detect this, scientists used a clever trick involving the cosmic microwave background. As the ancient light from the Big Bang passes through the hot gas of a massive galaxy cluster, it gets a slight energy boost. This is called the Kinetic Sunyaev-Zeldovich effect. By studying the subtle imprint this leaves on the microwave background, researchers could measure the cluster's motion through space. They analyzed hundreds of these distant clusters. The expectation was that their motions would be random, like individual leaves blowing in different directions. Instead, the data suggested a shocking coherence. Clusters scattered across billions of light-years seemed to be streaming together at speeds of millions of miles per hour, all toward the same patch of sky. The implications were staggering. For such a flow to exist, its source could not lie within our observable universe. Anything that massive inside our cosmic horizon would have been seen. This suggested the gravitational pull was coming from something beyond the edge of everything we can see. The frontier of the debate was immediately drawn. One camp argued this was evidence of a pre-inflationary relic, a scar from the universe's first moments that imprinted a direction on the cosmos before the rapid expansion of space began. An even more radical idea proposed the flow was a gravitational tug from a neighboring universe, a separate bubble of space-time brushing against our own in the greater multiverse. The other camp scrutinized the data itself. They questioned whether the signal was a statistical fluke, an artifact of how the measurements were processed, or perhaps contamination from other sources within our own galaxy. The controversy highlighted the raw, cutting-edge nature of cosmology. Dark flow sits at the very limit of what our instruments can perceive and our theories can explain. It forces us to confront a humbling possibility. The majestic cosmic flows we have mapped from the Great Attractor to the Shapley Supercluster might themselves be mere tributaries. They could be the local, visible branches of a river whose true source lies in an ocean of reality we cannot yet observe. Whether dark flow is ultimately confirmed as a real phenomenon or refined away by better data, its very proposal changes the questions we ask. It pushes our gaze past the horizon of light, wondering what unseen landscapes might be guiding the grandest currents of all. The controversy over dark flow forces a fundamental question. How do we trust a map of motion to reveal what we cannot see? The answer lies in a profound and elegant principle of physics. The observed flows of galaxies are not random. They are a direct, real-time readout of the invisible gravitational landscape of the cosmos. Every shift in velocity, every peculiar motion, is a galaxy responding to the collective pull of all the mass around it, both the stars we see and the vast, unseen reservoirs of dark matter. To understand this, picture a rolling hill covered in fresh snow. You cannot see the shape of the hill itself as it is buried, but if you release hundreds of marbles at the top, you can watch their paths. Some will roll straight down a steep slope, others will curve around a gentle ridge. By carefully mapping the speed and direction of every marble, you could reconstruct the entire hidden topography beneath the snow. This is precisely what cosmologists do with the universe. The marbles are the galaxies, the snow is the darkness between the stars, and the hidden hill is the gravitational potential, the sum total of all mass bending the fabric of spacetime. The mathematical relationship that makes this possible is deceptively simple in concept. In regions where mass is concentrated, like within a supercluster, gravity creates a deep well in spacetime. Galaxies naturally flow down into these wells, gaining speed as they go. Their velocity, therefore, becomes a direct measure of the slope and depth of the gravitational terrain they are crossing. By applying sophisticated techniques with names like potent analysis, scientists take the vast catalogue of galaxy motions, our map of the cosmic river, and run the equations in reverse. They start with the observed velocities and work backward to calculate the gravitational forces that must have caused them. This process is the ultimate act of cosmic cartography. It allows researchers to weigh colossal structures like the Shapley Supercluster from millions of light-years away, not by counting its visible stars, but by measuring how fiercely it tugs on everything around it. More importantly, it reveals the hidden architecture of the universe. The reconstructed gravitational map shows a web of dark matter filaments, immense rivers of invisible mass connecting galaxy clusters like beads on a string. It reveals vast, empty voids where the gravitational potential is flat and galaxies drift slowly, and dense supercluster knots where the potential plummets and galactic rivers converge. This conversion of motion into mass is our most powerful tool for seeing the unseen. It confirms that dark matter is not a vague idea but a tangible, mappable component of cosmic geography, its distribution etched into the very motion of the stars. We are no longer just watching galaxies move. We are using their journeys to illuminate the shadowy skeleton upon which the entire visible universe is built. So, if we can map this hidden mass with such precision, what does the final, complete picture tell us about the ultimate fate of our own galactic journey? This hidden gravitational landscape has a name and a shape. It is the cosmic web, the grand architecture of the universe on its largest scales. Picture an immense, three-dimensional spiderweb glistening with dew in the morning light. The thick strands of silk are the dark matter filaments. Where the strands intersect and knot together, you find the dense clusters and superclusters of galaxies, like the Shapley Supercluster. And between the strands, stretching for hundreds of millions of light-years, are the vast, nearly empty cosmic voids. This is not a static sculpture. It is a dynamic, flowing system, and the motion of galaxies reveals its currents with stunning clarity. The cosmic flows we have been mapping are not random drifts through empty space. They are channeled, directed movements. Galaxies stream along these invisible dark matter filaments like water, flowing through deep riverbeds, all rushing toward the gravitational lakes of the superclusters. This is why we see coherent bulk flows involving thousands of galaxies. They are not just being pulled toward a single point. They are traveling along the established highways of the web. To visualize this, scientists run immense computer simulations of the universe's evolution. They start with the near-uniform conditions just after the Big Bang, seed it with tiny ripples of dark matter, and let gravity do its work over billions of years of simulated time. The result is always a web. The dark matter clumps first into filaments, and ordinary matter, the gas that forms stars and galaxies, follows the gravitational blueprint, falling into those filamentary channels. When we compare these simulations to our real-world maps of galaxy positions, and crucially, their motions, the match is profound. The observed flows align almost perfectly with the predicted filaments of the simulated web. This is a powerful confirmation. We are not just inferring the web's existence from where galaxies sit. We are watching them move along its threads. Observational data from projects like the Sloan Digital Sky Survey allows us to paint this picture in reality. By plotting the positions and velocities of hundreds of thousands of galaxies, we can trace the streams. We see galaxies on the outskirts of a void moving slowly, almost drifting. Then, as they approach a filament, their speeds increase, caught in the gravitational current. Their motion accelerates as they travel along the filament toward a massive cluster, where many rivers of galaxies converge in a swirling, dense metropolis. This turns our understanding inside out. We once thought of clusters as the primary sources of gravity. Now we see they are merely the destinations. The true engines of large-scale motion are the filaments themselves, the great rivers of dark matter that define the contours of cosmic space. The flows are the dynamic expression of the web's gravitational architecture. Every peculiar velocity we measure is a galaxy responding to the slope of this hidden terrain. This concept changes a fundamental perspective. We are not just living in a galaxy within a cluster within a universe. We are living in a flow on a specific filament, traveling a specific route within an immense and structured cosmic geography. If these filaments are the rivers guiding all local motion, what happens when we zoom out to the very largest scale? Could the entire web itself be in motion, caught in a current far greater than any filament? But the cosmic web is not defined solely by where the mass is. Its true character is equally shaped by where the mass is not. Between the glittering filaments and dense clusters lie the cosmic voids, incomprehensibly vast regions of near emptiness that stretch for hundreds of millions of light years. These are not just passive gaps in the tapestry. They are active, dynamic players in the choreography of cosmic flows, and they exert their influence not by pulling but by pushing. To understand this, we must return to the Hubble flow, the smooth expansion of space itself. In a perfectly uniform universe, every galaxy would recede from every other at a speed perfectly proportional to its distance. But our universe is lumpy. In a dense supercluster, gravity is strong. It fights against the expansion, slowing it down locally and pulling galaxies together. Within a void, the opposite is true. With so little mass, there is almost no gravitational pull to counteract the relentless stretching of space. Here, the Hubble flow reigns supreme. The expansion proceeds faster inside a void than it does in the crowded filaments outside it. This creates a fascinating and counterintuitive effect. Imagine you are a galaxy sitting on the ridge between a deep valley and a high plateau. The valley is the void, a region where space is expanding more quickly. The plateau is the filament where expansion is slowed by gravity. From your perspective on the ridge, the floor of the valley is not just far away, it is actively falling away from you faster than the plateau behind you. You feel pushed away from the emptiness. This is precisely what happens to galaxies on the boundaries of cosmic voids. Their peculiar velocities do not point toward the nearest massive cluster. Instead, they point away from the center of the void. They are streaming outward, repelled by the accelerated expansion within the emptiness. This motion is a direct signature of the void's negative gravitational influence. By meticulously mapping the outward flow of galaxies around these empty regions, astronomers can trace the void's exact boundaries and even measure its internal dynamics. They can see how galaxies slowly drain out of the void over cosmic time, evacuated by the faster expansion within, adding to the rivers of galaxies flowing along the surrounding filaments. This turns our understanding of gravity on its head in a new way. We are accustomed to gravity as an attractive force, a pull. But on the scale of the cosmic web, the relative absence of gravity in a void creates a repulsive effect. It is the push of empty space. The void is not nothing. It is an active entity, a bubble of accelerated expansion that sculpts the motion of everything around it. So the grand flow of galaxies is not a simple tug of war between competing clusters. It is a complex dance directed by both the deep gravitational wells of superclusters and the expansive hills of the voids. Every galaxy's journey is a balance between being pulled toward mass and pushed away from emptiness. This complete picture of pulls and pushes woven into a web brings us to a final, profound question. If we can map all these motions with such precision, what does the ultimate destination of our own galactic river reveal about the fate of everything we see? The ultimate test of our cosmic maps lies in a digital universe, to see if our understanding of gravity, dark matter, and dark energy can truly explain the grand flows we observe. Scientists do not just look at the sky. They build a universe from scratch inside a supercomputer. These are cosmological simulations, vast numerical experiments with names like the Millennium Run and Illustris TNG. They begin with a simple, uniform sea of dark matter, sprinkled with the tiny quantum ripples from the Big Bang. Then they let the clock run forward. The simulation applies the unyielding law of gravity to billions, even trillions, of individual dark matter particles, all within an expanding space driven by dark energy. This is the standard model of cosmology known as Lambda-CDM. Over billions of simulated years, gravity amplifies those tiny initial ripples. Dark matter clumps into halos. Those halos merge and grow, and they trace out the familiar cosmic web of filaments and voids. But the simulation does not stop at a static picture. It records every step. At any moment in this virtual cosmos, the program knows the precise position and, crucially, the velocity of every single particle. This allows researchers to generate a predicted velocity field for the entire simulated universe. They can ask the computer to show them the bulk flows. They can trace the rivers of dark matter halos streaming along filaments toward massive clusters, and they can even simulate the repulsive push from the expanding voids. Then comes the critical comparison. Astronomers take this simulated map of predicted motions and lay it over the real map of observed galaxy flows from surveys like Sloan. The agreement is often breathtaking. The simulated universe, born from our equations of gravity and expansion, spontaneously generates the same kinds of coherent, large-scale flows we see in reality. It predicts the approximate speeds and the general directions. This is a profound validation. It tells us that the core physics in our models, the relentless pull of gravity acting on both visible and dark matter within an expanding space, is essentially correct. The cosmic river is not a mystery in principle. It is the natural, expected outcome of how structure grows in our universe. Yet the match is not perfect. Just as we see in the real data, the simulations sometimes struggle to produce the very largest, fastest flows observed at the farthest distances. The simulated rivers are there, but they might not run quite as deep or as swift as the ones we seem to measure. This lingering discrepancy is not a failure. It is the engine of discovery. It forces scientists to scrutinize every detail. Are the initial conditions of the simulation exactly right? Could there be even larger-scale structures beyond what our current models include? Or does this subtle tension point toward a need to refine our understanding of dark energy or gravity itself on the grandest scales? The digital universe is both a mirror and a laboratory. It reflects our current best understanding, and it provides a safe space to test what happens if we change the rules. By tuning the parameters and comparing the resulting flows to reality, we are not just mapping the cosmos. We are actively listening to it, using the motion of galaxies as a language to hear if our story of the universe needs a new chapter. That digital mirror reveals a critical blind spot in our mapping. Our most detailed charts of cosmic flows rely on galaxies we can see, which limits us to the relatively nearby universe. To test for currents on the grandest possible scale, like the controversial dark flow, we need a way to measure motion at distances where individual galaxies fade into obscurity. The solution comes from listening to the oldest sound in the universe and hearing how it changes as it passes through the giants of the cosmos. It is called the Kinetic Sunyaev-Zeldovich effect, and it is one of the most delicate measurements in all of astronomy. The principle is rooted in a simple, everyday experience. Think of the sound of a train whistle. As the train moves toward you, the sound waves are compressed, raising the pitch. As it moves away, the waves are stretched, lowering the pitch. This is the Doppler effect, and it applies to light just as it does to sound. Now, imagine the train is not a locomotive, but an entire galaxy cluster, a city of 1,000 galaxies filled with gas hotter than the core of a star. And imagine the sound is not a whistle, but the ancient whisper of the cosmic microwave background, the afterglow of the Big Bang itself. As these primordial CMB photons travel across the universe, they occasionally pass directly through one of these massive clusters. The hot electrons in the cluster's gas interact with the photons, giving them a tiny nudge. If the cluster is moving toward us or away from us along our line of sight, that nudge imparts a minuscule Doppler shift onto the photons. This is the Kinetic Sunyaev-Zeldovich effect. It leaves an incredibly subtle imprint on the CMB's temperature in the precise direction of the cluster. The shift is vanishingly small, a change of just a few millionths of a degree in a signal that is already 270 degrees below zero. Isolating this signal from the cacophony of other cosmic foregrounds is like trying to hear a single, specific leaf rustle in a hurricane. Yet this tiny whisper is a goldmine of information. Unlike methods that rely on a galaxy's distance, the KSZ effect is distance independent. It does not matter if the cluster is 500 million or 5 billion light-years away. The size of the temperature shift depends only on the cluster's line of sight velocity and the density of its hot gas. This makes it a direct speedometer for the most massive structures in the universe, even at the very edge of the observable cosmos. By applying this technique to hundreds of distant clusters, astronomers can construct a velocity map on a truly cosmic scale. They are not looking at the motion of stars within galaxies, but at the bulk motion of these colossal clusters themselves, each one a gravitational anchor for thousands of galaxies. This is how scientists probe the dark flow hypothesis. They stack the KSZ signals from many clusters spread across the sky, looking for a common directional bias in their motions. A coherent flow on such scales would be the signature of something immense pulling from beyond our horizon. Whether the final data confirms or refutes such a flow, the Kinetic Sunyaev-Zeldovich effect has already opened a new window. It extends the river map into the deep past, allowing us to ask if the cosmic currents we see today have always flowed in the same direction, or if the universe's grand geography reshapes itself over eons. That subtle tension between the map and the ancient light points toward a deeper, more fundamental question: is the universe truly the same in every direction? For centuries, a bedrock principle of cosmology has been the cosmological principle. It states that on the largest scales, the universe is both isotropic and homogeneous. Isotropic means it looks the same in every direction. Homogeneous means matter is evenly distributed when you take a big enough step back. It is the idea of cosmic fairness, that no place and no direction is special. This principle is the foundation upon which our entire model of the Big Bang and cosmic expansion is built. Yet, the very existence of coherent, continent-sized flows of galaxies, all moving in concert across billions of light-years, whispers a challenge to this foundational idea. It suggests the universe might not be perfectly fair. It might, in fact, be lopsided. Scientists call this lopsidedness anisotropy, a preferred direction in the fabric of reality itself. The evidence for this grows stranger the deeper we look. Beyond the bulk flows, astronomers have reported other curious alignments that seem to defy the expectation of randomness. Some studies of distant quasars, the brilliant cores of ancient galaxies, suggest their rotational axes might not be randomly oriented across the sky. Instead, they appear to show a subtle preference, as if countless spinning tops across the cosmos were all nudged to tilt in a similar direction. Other research has examined the polarization of light from the cosmic microwave background, searching for patterns that might indicate a preferred cosmic axis, a kind of spine to the universe. Perhaps most startling is the concept of a cosmic dipole, not just in our motion, but in the very distribution of galaxies themselves. If you divide the sky into two hemispheres, one might contain slightly more galaxies or more massive clusters than the other. This would not just be a current in the river, but a permanent tilt to the entire riverbed. The implications of confirming such a large-scale anisotropy are profound. It would mean that the initial conditions of the Big Bang were not perfectly smooth and symmetric. There was a seed, a primordial fingerprint, that imprinted a direction onto the infant cosmos, and that direction has echoed through 14 billion years of expansion, still visible in the aligned spins of quasars and the streaming of superclusters. This could point to exotic physics operating in the universe's first fleeting moments, forces or fields that broke symmetry in a fundamental way. Some theories even suggest it could be a relic of our universe brushing against another in a greater multiverse, a cosmic bruise left by a collision with a neighboring reality. Yet the scientific community approaches these claims with rigorous caution. The signals are incredibly faint, sitting right at the edge of statistical significance. Could these alignments be a trick of the data, a selection bias in how we observe the sky, or simply a colossal cosmic coincidence? The debate is fierce and essential. It represents the very process of science confronting its own assumptions. Every new, deeper survey of the sky is a test. Researchers are now using missions like the European Space Agency's Planck satellite and ground-based telescopes, mapping millions of galaxies to search for or definitively rule out these universal asymmetries. They are asking the cosmos a direct question: are you truly isotropic, or have we begun to see the contours of a grander, more textured reality? The answer will not just tell us which way the river flows, but whether the river itself runs through a perfectly round valley or one with ancient, sloping walls. Our two most trusted cosmic compasses are pointing in slightly different directions. This is the dipole discrepancy, a precise and puzzling tension at the heart of modern cosmology. On one hand, we have the galaxy frame. By meticulously mapping the gravitational pull of every major structure we can see, the Great Attractor, the Shapley Supercluster, the surrounding filaments and voids, we can calculate our expected motion through the cosmos. This gives us a predicted speed and direction. On the other hand, we have the cosmic microwave background frame. The temperature dipole in that ancient light acts as the universe's ultimate rest frame, a fixed benchmark against which all motion is measured. It gives us our observed speed and direction. In a perfectly mapped universe, these two numbers would match exactly. They do not. The mismatch is small but significant, a difference of a few tens of kilometers per second and a shift of several degrees in the sky. To a cosmologist, this is not a minor detail. It is a clue. One leading hypothesis is that our catalogue of cosmic giants is still incomplete. Perhaps there are enormous concentrations of mass, even larger than the Shapley Supercluster, lying just beyond the current limits of our deepest galaxy surveys. Their gravitational influence would already be tugging on us, but their light has not been fully mapped into our three-dimensional charts. We would feel their pull before we see their form. This unseen mass would add an extra vector to our motion, one not yet accounted for in our galaxy-based calculations, explaining why the CMB measures a slightly different flow. Another possibility points closer to home. Could there be significant local structures within our own galactic backyard that we have underestimated? Vast clouds of intergalactic gas or diffuse halos of dark matter associated with our local filament could be adding a subtle, unmodeled push or pull. Our maps of the very nearby universe are incredibly detailed, but they are not perfect. A hidden gravitational hill or valley within a few 100 million light-years could easily skew our calculations. Then there is the question of depth. Our galaxy surveys, while immense, still have a horizon. They map a fantastic volume of space, but it is a finite volume, like taking a core sample from the ocean floor. The currents we measure within that sample might be influenced by tides originating from deeper, darker waters we have not yet reached. If the true cosmic flow is shaped by structures on scales larger than our survey, our local map will inevitably be incomplete, leading to a discrepancy with the universal CMB benchmark. Of course, scientists must also rigorously consider a more mundane explanation. Could this be a systematic error? Measuring galaxy distances and velocities across hundreds of millions of light-years is an exercise in managing countless tiny uncertainties. The calibration of instruments, the modeling of galactic dust, the assumptions built into our distance calculations, any of these could introduce a collective bias that manifests as this subtle directional tension. Teams across the globe are constantly cross-checking their methods, using independent surveys and novel techniques to hunt for any hidden flaw in the measurement process. Resolving the dipole discrepancy is not an academic exercise. It is the essential work of creating a fully consistent map of our place in the cosmos. It forces us to ask whether we have truly seen all the major landmarks in our cosmic neighborhood, or if we are still missing a continent on our map. Each new, deeper galaxy survey brings us closer to an answer. Projects like the Dark Energy Spectroscopic Instrument are mapping tens of millions of galaxies, extending our gravitational sensors to unprecedented depths. With this richer data, we can perform a more complete accounting of all the pulls and pushes acting on our local group. The outcome holds weight for our fundamental models. If the discrepancy vanishes with better data, it will be a triumphant validation of our understanding, proof that Lambda-CDM cosmology can account for all motion, from the smallest galaxy to the largest flow. But if the tension persists even as our maps improve, the implications are far more thrilling. It would be a direct signal that something in our standard model is incomplete, perhaps hinting at new physics governing gravity or the large-scale structure of space itself. This tiny arrow of disagreement, therefore, is not a flaw in our science. It is a guidepost pointing our gaze toward the next frontier of cosmic discovery. The resolution to these cosmic puzzles will be written in light we have not yet collected. Our current maps, revolutionary as they are merely the first sketches of a continent we are only beginning to explore. They are built from the positions and motions of millions of galaxies. The next generation of observatories will chart billions, transforming a detailed regional survey into a complete atlas of the observable universe. This leap in scale will redefine our understanding of cosmic flows, tracing their origins across time and space with unprecedented clarity. Leading this charge are three monumental projects, each designed to see the cosmos in a new way. The Vera C. Rubin Observatory, perched atop a mountain in Chile, will soon begin the legacy survey of space and time. Its enormous mirror and gigantic camera will scan the entire southern sky every few nights for a decade, not once but over and over. This is not about taking a single snapshot. It is about creating a cosmic movie. By detecting subtle changes in the brightness of billions of galaxies, the LSST will allow astronomers to measure their distances and, by extension, their peculiar velocities with a statistical power that dwarfs all previous efforts combined. It will map the local flow field in stunning high definition, revealing every tributary and eddy in our cosmic river. Simultaneously, the European Space Agency's Euclid mission is viewing the cosmos from a vantage point beyond Earth's atmosphere. Euclid's specialty is cosmic shear, the subtle warping of galaxy shapes by the gravitational lensing effect of dark matter. While it meticulously charts the distribution of this invisible mass, it will also pinpoint the redshifts of over 1 billion galaxies. This dual capability is key. Euclid will provide an independent, exquisitely precise three-dimensional map of both the mass and the galaxies, allowing scientists to directly compare the gravitational landscape with the flow of galaxies moving through it. This will test the fundamental link between gravity and motion with a rigor never before possible. Then there is the Square Kilometre Array, a revolutionary radio telescope being built across 2 continents. The SKA will not see visible light. Instead, it will listen to the universe. It will detect the faint radio emission from neutral hydrogen gas, the raw material of stars which permeates galaxies and the space between them. This allows it to map structures completely hidden from optical telescopes, piercing through cosmic dust. Crucially, the SKA can measure the redshift of this hydrogen with phenomenal accuracy, providing a direct, clean measurement of galaxy velocities across vast cosmic distances. Its view will extend so deep into space, and therefore back in time, that it will allow us to see how cosmic flows have evolved over billions of years. Have the great rivers always streamed toward Shapley, or did they once flow in different directions toward ancient superclusters that have long since merged and dispersed? Together, these instruments will create a flow map of the universe in high fidelity and in 3 dimensions across cosmic time. They will provide the data to either confirm or finally lay to rest the tantalizing hints of dark flow. If a coherent motion of distant clusters truly exists, these surveys will see it with undeniable statistical certainty. They will also deliver a definitive verdict on large-scale anisotropy, measuring the distribution of galaxies and clusters across the entire sky to determine, once and for all, if the universe possesses a hidden spine or axis. The coming decade of data will not just answer old questions. It will undoubtedly reveal new patterns, new currents, and new structures that we cannot yet conceive, each one a clue to the forces that have shaped everything from the largest supercluster to our own galactic home. These immense new maps will generate a flood of data unlike anything in the history of science. The Vera Rubin Observatory alone will produce over 20 terabytes of information every single night, a torrent of light and numbers that would take a human researcher thousands of lifetimes to sift through. To find the subtle signatures of cosmic flows within this ocean of data, cosmologists are turning to a new kind of partner, artificial intelligence. Machine learning algorithms are being trained to see the universe in ways we cannot, to decode the hidden patterns in the motion of galaxies and reconstruct the invisible architecture that guides them. This is not about replacing scientists, but about giving them superhuman eyes. An algorithm can be shown millions of simulated universes, each with a known velocity field and a known underlying dark matter web. It learns the complex, non-linear relationships between the two. It learns what a filament's gravitational signature looks like in the peculiar velocities of the galaxies flowing along it. It learns to recognize the subtle statistical whisper of a vast, distant supercluster pulling on everything in its vicinity. Then, when presented with the real observational data, the algorithm can perform a task that is incredibly difficult with traditional statistics. It can separate the cosmic signal from the observational noise with astonishing efficiency, isolating the true flow of the river from the ripples caused by measurement uncertainty. Think of it as listening to a crowded room. Your human ear might struggle to pick out a single conversation across the noise. A machine learning model, trained on countless hours of similar audio, can isolate that one voice, filter out the clatter, and transcribe the words with perfect clarity. In cosmology, the voice is the coherent motion of galaxies, and the clatter is everything from dust in our own galaxy to instrumental errors. These AI tools are already being used to reconstruct the cosmic web directly from galaxy surveys. Instead of relying on simplified assumptions, the algorithms can take a raw catalog of galaxy positions and redshifts and output a three-dimensional map of the most probable dark matter filaments and voids, along with a prediction of how galaxies should be flowing through that landscape. When compared to the actual observed motions, any discrepancies become bright red flags for new discoveries. Perhaps the model predicts a gentle flow in one region, but the data shows a raging current. That mismatch could point to a hidden concentration of mass, a previously unknown giant lurking in the shadows of our map. The promise of this approach is a new era of pure, data-driven discovery. Machine learning does not start with a preconceived theory of what should be there. It simply asks the data to reveal its own deepest patterns. It might uncover strange, twisted correlations in the velocity field that human analysts would never think to look for, suggesting entirely new types of large-scale structure or novel interactions between dark matter and dark energy. These algorithms are the essential cartographers for the next cosmic atlas, translating the raw numbers of 1 billion galaxy redshifts into a dynamic, flowing portrait of our universe's hidden skeleton. With such powerful tools to chart the currents, we must finally ask where this grand river is ultimately taking us. What is the final destination for our galaxy and for the cosmic web itself? The ultimate fate of our cosmic river is not written in gravity alone, but in the silent, pervasive pressure of the void itself. This is the domain of dark energy, the mysterious force causing the expansion of the universe to accelerate. While gravity tirelessly works to pull matter together, weaving the cosmic web and channeling the great flows, dark energy acts in opposition, stretching the very fabric of space and pushing the web apart. This cosmic tug of war between attraction and repulsion does not just determine the universe's final destiny, it leaves its fingerprints on the motion of galaxies we observe today. To understand how, picture a river system on a planet where the gravity is slowly weakening. Over time, the water's current would slow, the channels would widen and become shallower, and the entire network would grow more diffuse. Dark energy has a similar effect on cosmic flows. In the early universe, when matter was denser and dark energy's influence was negligible, gravity ruled supreme. Structures grew rapidly, and the rivers of galaxies flowed swiftly down steep gravitational slopes into the waiting clusters. But as the universe expanded and diluted, dark energy's repulsive push began to dominate. It acts as a cosmic friction, resisting gravity's pull and slowing the growth of new structure. Consequently, the development of new bulk flows, the emergence of new rivers has been stifled over the past several billion years. The most powerful flows we see today are ancient relics, their currents established in an era when gravity's grip was far stronger. This gives astronomers a powerful new tool. By mapping the velocity field of galaxies at different distances, which correspond to different epochs in cosmic history, we can measure how quickly flows were growing in the past compared to now. We can look at galaxies 5 billion light-years away and measure the coherence and speed of their bulk motions. Then we compare that to the flows we see in our local, modern universe. If dark energy is indeed accelerating expansion, we should see a clear signal. The older, more distant flows should appear stronger and more coherent, like youthful, raging rivers. The flows in our recent cosmic neighborhood should be more subdued, like mature, slower-moving waterways. This comparison turns the motion of galaxies into a direct probe of dark energy's strength and evolution. It provides a crucial independent test, completely separate from the methods that first discovered cosmic acceleration, like observations of distant supernova or subtle patterns in the cosmic microwave background. Those techniques measure the expansion history of space itself. Studying cosmic flows measures how that expansion history has impacted the growth of the universe's structure, the very skeleton upon which the flows travel. A discrepancy here would be revolutionary. If the observed slowing of flow growth does not match the predictions based on our standard model of dark energy, it could mean this mysterious force is not a constant, as in Einstein's cosmological constant, but something that changes over time, a dynamic field with properties we have yet to imagine. The implications for the universe's fate are profound. A constant dark energy leads to a forever accelerating, increasingly lonely cosmos where distant flows are eventually stretched apart and frozen. But a changing dark energy could open other possibilities, perhaps even a future where the repulsive force weakens, allowing gravity to once again gather the scattered fragments of the cosmic web. By charting the rivers of galaxies across time, we are not just mapping where we have been, we are reading the current for clues about where the entire cosmos is ultimately flowing. Our galactic river presents a profound challenge to our deepest understanding of gravity itself. Every map we have created, every current we have charted, relies on a single, towering assumption, that Einstein's theory of general relativity and Newton's laws before it are perfectly correct on the grandest scales. But what if the river is not revealing hidden mass? What if it is revealing a flaw in the law of gravity? A small but persistent group of physicists proposes exactly this. They argue that the observed motions of galaxies, the very coherence of the cosmic flows, might not require dark matter at all. Instead, they suggest our theory of gravity is incomplete and needs modification. The leading alternative is known as modified Newtonian dynamics, or MOND. Its core idea is elegantly simple. In the extremely weak gravitational fields found in the outer reaches of galaxies and in the vast spaces between them, gravity behaves differently than Newton or Einstein predicted. It becomes slightly stronger. Under MOND, a galaxy's rotation curve, the way its stars orbit the center, flattens out not because of an invisible halo of dark matter, but because the force of gravity itself does not fade as quickly with distance as our standard formulas say it should. This single adjustment can beautifully explain the motions of stars within individual galaxies without invoking any unseen particles. But the true test of any theory of gravity is whether it can scale up. Can it explain the great bulk flows, the coordinated motion of thousands of galaxies across hundreds of millions of light years? This is where MOND and its relativistic extensions face their greatest trial. In our standard model, these flows are a direct consequence of the gravitational pull from immense, mappable concentrations of both visible and dark matter. The river exists because of the sloping terrain of the cosmic web. In a MOND universe, the explanation must be different. Without dark matter halos and filaments, what could possibly create such coherent, large-scale motion? Proponents have developed sophisticated computer simulations within modified gravity frameworks. Their results are intriguing. They show that in a MOND universe, the gravitational influence of a massive object like a galaxy cluster extends much farther than in standard gravity. The sphere of influence of a supercluster becomes vastly larger. This means that a structure like the Shapley Supercluster could, in theory, exert a significant gravitational pull on galaxies far beyond the range predicted by general relativity. In this view, the cosmic flow is not a river channeled by hidden dark matter banks, but a tide raised by a visible but extraordinarily far-reaching giant. The debate is fierce and fundamentally important. It turns cosmic flows into a laboratory for the laws of physics. Each new, precise map of galaxy motions provides data that can be used to test the predictions of both theories. For instance, the detailed relationship between the distribution of visible galaxies in a filament and the peculiar velocities of the galaxies within that filament could have a distinct signature in MOND versus standard gravity. The way flows evolve over cosmic time might also differ. The ongoing challenge for modified gravity is to not just match one observation, but to explain the entire suite of cosmic data. From the cosmic microwave background to the clustering of galaxies to the very existence of the cosmic web, all within a single, consistent framework without dark matter. So far, the standard model of cosmology with dark matter and dark energy has proven remarkably resilient, providing a unified explanation for phenomena across the entire history of the universe. Yet, the persistence of the modified gravity community ensures that our assumptions are constantly stress-tested. They remind us that the cosmic river is more than a current of galaxies. It is a flow of information carrying signals about the most fundamental forces shaping reality. Whether the final explanation rests on unseen matter or a refined law of physics, the journey to understand it is pushing the very boundaries of human knowledge. This immense tug-of-war between gravity and dark energy might be playing out right in our own cosmic backyard, but with a surprising twist. The very ground beneath our feet, or rather, the space around our galaxy, might not be what we thought. Some cosmologists propose we are living in a cosmic anomaly, a vast bubble of relative emptiness known as the KBC Void. This idea, stemming from the work of astronomers Keenan, Barger, and Cowie, suggests our local universe is not a representative sample. Instead, we may be floating in a region of space that is startlingly sparse, a void spanning over 1 billion light-years that is roughly 7 times emptier than the cosmic average. This is not a small pocket of space. It is a gaping chasm on a continental scale, and if it is real, it fundamentally reshapes how we interpret our own motion. Within such a void, the rules are different. With so little mass to provide gravitational attraction, the dominant force is the accelerated expansion driven by dark energy. Space inside the void stretches faster than it does in the denser regions outside it. Think of it like standing on a sheet of rubber that is being pulled taut. If you are standing on a thick, reinforced section, you feel little movement. But if you are standing on a thin, weak patch, you feel it stretch rapidly beneath your feet. In this analogy, our galaxy is on that thin patch. The faster expansion inside the KBC void creates a powerful repulsive effect. Galaxies on the boundary, including our own, are not being pulled toward a massive attractor from one direction so much as they are being pushed outward from the void's center in all directions. This outward flow would be a major contributor to our observed peculiar velocity, that 600 km/s journey we are on. It would mean a significant portion of our motion is not a tug toward Shapley, but a push away from an immense local nothingness. The implications of this are profound for all of cosmology. For decades, we have assumed our position in the universe is ordinary, that we see a fair and average slice of cosmic reality. This principle allows us to take local measurements, like the expansion rate we see from nearby supernova, and apply them to the entire cosmos. But if we are sitting in a giant underdensity, that assumption crumbles. Our local measurements of the Hubble constant, the rate of the universe's expansion, would be skewed. From inside an expanding bubble, everything outside the bubble would appear to be rushing away faster than it truly is on a global average. This could explain a portion of the persistent tension between different methods of measuring the Hubble constant, one of the most pressing puzzles in modern cosmology. Confirming or refuting the KBC void is therefore not just an academic curiosity. It is an essential act of cosmic calibration. It asks us to check our address to see if our window on the universe looks out onto a typical street or a uniquely quiet cul-de-sac. If we are in a void, then our maps of cosmic flows need a crucial correction, subtracting this local push to see the true pull of the distant giants. It reminds us that to understand the river, we must first understand the shape of the valley we are standing in. We have always sought a fixed address in the universe, a stationary home from which to observe the stars. This new cosmic map offers a profoundly different truth. Our place is not a fixed point, it is a trajectory. We are passengers on a galactic vessel sailing a river whose source we are still tracing, and this realization completes a centuries-long journey of cosmic humility. For millennia, humanity placed itself at the very center of creation. Earth was the unmoving stage around which the sun, planets, and stars dutifully revolved. That geocentric model was more than an astronomical error. It was a philosophical anchor, assuring us of our singular importance in the grand design. The work of Copernicus, Galileo, and Kepler shattered that anchor. They showed Earth was not the center, but a planet orbiting an ordinary star. This was the first great cosmic demotion, a shift so profound it redefined our entire relationship with the heavens. We moved from the center to a suburb, yet even in that Copernican revolution, a comforting stillness remained. Our sun, and by extension our planet, was imagined as a relatively fixed point in a stable celestial neighborhood. The discovery of cosmic flows has now taken that remaining comfort away. Our sun is not fixed. Our galaxy is not at rest. We are caught in a current of staggering scale, moving at over 1 million miles per hour toward a horizon defined by invisible giants. This is the second great demotion, not of position but of rest. We are not even motionless residents of the cosmic suburb. We are transients rushing through it. This shifts our philosophical perspective from one of static location to one of dynamic journey. Our destiny, on the grandest scale, is tied to this flow. In time, billions of years from now, the Milky Way and all the galaxies of our local stream will merge into the vast metropolitan glow of the Shapley Supercluster, drawn together by gravity's patient pull. Our distant descendants, should any exist, will gaze upon a night sky utterly transformed, filled with the blended light of 100,000 galaxies in a single, crowded celestial city. This future is written in the velocity we measure today. So what does this mean for our sense of place? It replaces the loneliness of a static island with the connection of a shared voyage. Every galaxy in our local stream, every star within them, is a fellow traveler on this same current. We are part of a collective migration, a grand procession of matter across the cosmos. This shared motion creates a new kind of cosmic kinship, linking us not by proximity, but by a common destination and a common history of falling through space for billions of years. It also injects a powerful sense of scale into our daily lives. The concerns of our world are real and immediate, yet they unfold on a speck of rock carried by a star, which is carried by a galaxy, which is itself carried by a river of galaxies flowing across the universe. This layered reality does not diminish our human experience. It frames it within an epic narrative of almost unimaginable scope. We are simultaneously the authors of our own tiny stories and bit players in a cosmic story whose full script we are only beginning to read. The drive to map these flows, then, is more than scientific inquiry. It is the latest chapter in humanity's oldest quest to understand where we are and where we are going. From ancient navigators using stars to cross oceans, to modern astronomers using redshift to chart galactic currents, the impulse is the same: to find our bearing in the vastness. Each new map, each refined measurement of our motion, is another point plotted on that grandest of charts. It tells us we are not adrift, but journeying with purpose along a course laid down by the very architecture of the universe. The river has a source, and we are flowing toward it. That knowledge, humbling and exhilarating, forever changes our address in the cosmos. These maps of motion transform from abstract data into breathtaking journeys through the use of innovative visualizations. One of the most powerful tools for this is the digital planetarium show. In domes across the world, audiences are no longer simply looking at a static star field. They are taken on a flight that begins within our own Milky Way, then pulls back at an accelerating pace. The familiar constellations dissolve, replaced by a growing three-dimensional pointillism of galaxies. Then the magic happens. Each point of light begins to trail a streak, a vector that shows its direction and speed. What was a cloud of random dots becomes a flowing, organized system. You see the local group moving as a unit. You witness the great rivers of galaxies converging toward superclusters, and you feel the scale of the voids pushing everything outward. This visual translation of velocity fields into a visceral, navigable experience is fundamental. It allows anyone, regardless of scientific background, to intuitively grasp the coordinated motion that raw data can only describe. The feeling is not of learning a fact, but of witnessing a truth about the cosmos' dynamic nature. Beyond the planetarium, interactive online simulations have become a revolutionary tool for engagement. Projects like the Universe in a Box simulations hosted by universities and science websites invite the public to play the role of a cosmic architect. A user can adjust parameters, perhaps increasing the density of a simulated dark matter filament, and then press play to watch billions of years of cosmic evolution unfold in seconds. They see how tiny initial ripples grow under gravity, how filaments naturally form, and most importantly, how galaxies begin to stream along those invisible highways. By giving someone the controls, the simulation demystifies the process. It shows that the great flows are not magical or arbitrary, but the inevitable, beautiful consequence of simple physical laws acting over immense timescales. Another powerful example is the Sloan Digital Sky Survey's Public Data Explorer, which allows users to visually filter millions of real galaxies by distance and direction, creating their own slices of the cosmic web and seeing the large-scale structures that channel motion. These visualizations do more than educate, they create a sense of shared discovery. When you manipulate a digital universe and see a bulk flow emerge from your own adjustments, you are not just being told a story, you are participating in the reasoning that led to its discovery. This builds a deeper, more personal connection to the science. It transforms the cosmic flow from a distant curiosity reported by experts into a tangible pattern that anyone can observe and understand. The ultimate goal of these tools is to bridge the gap between the monumental scale of the data and the human scale of perception. They turn redshift numbers and velocity vectors into a symphony of motion, allowing us to see and almost feel the current that carries our galaxy. This shared visual language prepares us for the next logical step, not just observing the flow, but asking what we might one day learn by riding it. The great maps of cosmic flow are built not by machines alone, but by the collective curiosity of millions of human eyes. This vast endeavor of cosmic cartography faces a fundamental challenge: the sheer, overwhelming volume of data. Modern sky surveys capture images of hundreds of millions of galaxies, each one a potential data point for our velocity maps. To understand their role in the cosmic web, we must first know what they are, their shapes, their orientations. No team of professional astronomers, no matter how large, could ever hope to classify them all. This is where the story takes a beautifully human turn with the rise of citizen science. Projects like Galaxy Zoo have opened the vaults of the universe to anyone with an internet connection and a sense of wonder. The premise is elegantly simple. A volunteer logs on and is presented with a real, often never-before-seen image of a galaxy from a telescope like the Sloan Digital Sky Survey. Their task is straightforward: to answer a few basic questions. Is the galaxy smooth and round, or does it have a disk and spiral arms? Is it edge-on or face-on? Is there anything odd or unusual about it? In just a few clicks, a person sitting at a kitchen table or in a library becomes a cosmic classifier, contributing directly to the largest catalog of galactic morphology ever assembled. This collective effort is far more than a helpful crowd-sourced task. It is foundational science. The shape and type of a galaxy tell us about its history, its environment, and its likely motion within the cosmic web. Spiral galaxies, for instance, are often found in the quieter suburbs of Filaments, while elliptical galaxies congregate in the dense, violent cores of clusters where gravitational interactions are fierce. By classifying millions of galaxies, volunteers are helping to paint the detailed portrait of the cosmic landscape through which the great flows travel. Their work provides the essential context that turns a dot of light in a survey into a character with a story in the grand narrative of structure formation. Perhaps the most thrilling aspect of this collaboration is the human capacity for pattern recognition, which even the most advanced algorithms cannot yet match. The human eye is exceptionally good at noticing the unusual, the outlier, the thing that does not fit. Volunteers in these projects have made legitimate, published discoveries that machines programmed to find common patterns simply overlook. They have identified rare galactic mergers, strange gravitational lenses, and entirely new classes of objects, like the now famous green pea galaxies, compact star-forming systems that offer clues about the universe's early years. Each of these discoveries can refine our models. A newly found cluster or a peculiar galaxy group adds another landmark to our gravitational map, helping to explain why galaxies in a certain region might be streaming in a particular direction. The river map gains resolution not just from petabytes of data, but from moments of human insight scattered across the globe. This transforms the quest from a remote, technical exercise into a shared human adventure. It democratizes the exploration of the cosmos, proving that the drive to understand our place in the universe is a universal trait. Every classification submitted is a vote of curiosity, a small stitch in the vast tapestry of collective knowledge. As these catalogs grow from millions to billions of entries with new telescopes coming online, this partnership will only become more vital. The river of galaxies flows on, and now, thanks to this global network of observers, we have countless more guides helping us to chart its course, reminding us that the cosmos is not just something we look at, but something we are all a part of exploring together. The river of galaxies is charted by a new kind of cartographer. The astrophysicist who maps its currents no longer works in isolation with a telescope, but as part of a vast, interconnected network of minds. To decipher the subtle signals of bulk flows, they must become fluent in the languages of advanced statistics, fluid dynamics, and high-performance computing. This is where the study of cosmic motion transcends a single science and becomes a grand, interdisciplinary symphony. At its core, the mathematics describing the flow of thousands of galaxies is startlingly similar to the equations that model the flow of water in an ocean current or the circulation of air in a planetary atmosphere. Cosmology, in a very literal sense, studies the behavior of a fluid, a cosmic fluid where the particles are galaxies and the driving force is gravity. Experts in fluid dynamics from fields like meteorology and oceanography now collaborate with cosmologists, bringing sophisticated tools developed to predict weather patterns or track deep-sea currents. These tools are adapted to model how density ripples in the early universe evolved into the swirling, channeled rivers of galaxies we see today. The techniques for filtering signal from noise in a chaotic oceanographic dataset are remarkably effective at isolating the coherent flow of a supercluster from the random motions of individual galaxies. Meanwhile, the challenge of handling petabytes of galactic data falls to the data scientists. The algorithms they design to detect subtle correlations in financial markets or to parse patterns in global social networks are retrained on the cosmos. Machine learning models that can spot a fraudulent transaction among millions are taught to identify a hidden filamentary structure in a galaxy survey, or to predict the peculiar velocity of a galaxy based on its environment. This cross-pollination accelerates discovery, allowing techniques refined over decades in other fields to be applied almost overnight to the universe's grandest puzzles. High-performance computing provides the stage for this collaboration. The simulations that recreate cosmic evolution require the world's most powerful supercomputers, machines also used for climate modeling, pharmaceutical discovery, and aerospace engineering. The same code that simulates airflow over a wing might be adapted to model dark matter streaming along a filament. A cosmologist might sit beside a computational chemist, both leveraging unimaginable processing power to visualize the invisible architecture of their respective worlds, one subatomic, the other galactic. Finally, data visualization artists and designers translate these immense numerical outputs into the planetarium shows and interactive models that allow us to see and feel the cosmic flow. Their skill in making complex data intuitive and beautiful is what turns abstract velocity vectors into a breathtaking flight through the streaming web. This melting pot of disciplines reveals a profound truth about modern exploration. The universe's greatest mysteries are no longer solved by a lone genius with a telescope. They are unraveled by teams of specialists, speaking different technical languages but united by a shared curiosity, each borrowing a tool from their field to help map a small section of the river. The flow of galaxies inspires a parallel flow of ideas, reminding us that to understand the cosmos, we must first learn to connect with each other. The most beautiful maps are those with edges still blank, marked only by the words "Here be dragons." Our current atlas of cosmic flows is precisely such a map, its most compelling features being the unsolved mysteries that linger at its borders. The first and most profound of these is the question of dark flow. Is the apparent stream of distant galaxy clusters a real, universal current, or a statistical mirage born from the immense challenge of measuring such subtle signals? The answer remains suspended, awaiting the torrent of data from the next generation of observatories. Its resolution carries immense weight, for if confirmed, dark flow would point to influences from beyond our cosmic horizon, perhaps even brushing against the radical idea of a multiverse. Then there is the persistent dipole discrepancy, that stubborn mismatch between the motion we measure from ancient light and the motion we predict from mapped mass. This tiny arrow of disagreement is a whisper that our gravitational census is incomplete. It begs the question of what unseen continent of mass, what hypercluster beyond Shapley, might be exerting a pull we feel but cannot yet see. Could there be flow patterns on scales so vast they encompass the entire observable universe, patterns our current surveys are simply too small to capture? Each deeper map we make reveals not just answers, but new, more refined questions. Some theorists wonder if the specific alignments within these flows could be a fossil, an imprint from the universe's birth in a pre-Big Bang state, a relic of physics operating at energies we can never directly recreate. These are not failures of understanding, but the signposts of a living, breathing science. They are the dragons on the map, the unknowns that propel the next expedition. Every mystery in flow cosmology is a promise that the universe still has secrets to share, ensuring that our journey to understand the great river of galaxies is an adventure with no end in sight. Our cosmic address received a stunning update in 2014. Before then, we thought we lived in a modest neighborhood called the Virgo Supercluster, a loose gathering of galaxy groups centered on the Virgo cluster. But a new map, drawn not by static location but by the flow of galaxies, revealed our true home to be far grander and more dynamic. Astronomers named it Laniakea, a Hawaiian word meaning immense heaven. This was not just a new label, it was a fundamental shift in how we define these colossal structures. Traditionally, superclusters were identified by density, simply grouping together galaxies that appeared close to one another in the sky. The team, led by astronomer R. Brent Tully, used a different principle entirely, one borrowed from Earth's own geography. They defined Laniakea by its watershed. Just as every raindrop in the Mississippi River basin flows toward the Gulf of Mexico, every galaxy within Laniakea's bounds is flowing toward the same gravitational center. That center is the Great Attractor region, the dense, obscured hub that had puzzled scientists for decades. Using the precise velocity measurements from thousands of galaxies, the researchers charted the local cosmic velocity field in exquisite detail. They traced the paths of galactic motion like a hydrologist tracing streams down a mountainside. Where the flows diverged, they marked a boundary. All the streams that converged inward toward the Great Attractor's gravitational well were declared part of the Laniakea Basin. The map that emerged was breathtaking. Laniakea is a filamentary spiderweb of staggering scale, spanning over 500 million light-years. It contains roughly 100,000 galaxies, including our own Milky Way, all bound by the shared destiny of their motion. The Virgo cluster, once thought to be our supercluster's heart, was revealed to be just a peripheral suburb, a tributary flowing into the much larger Laniakea River. This redefinition is the ultimate validation of flow mapping. It proves that to understand cosmic structure, you must watch it move. A static snapshot shows you where things are, but it cannot reveal to which community they truly belong. Two galaxies might appear close together in the sky, but if their velocity vectors show one is flowing toward a different gravitational basin, they are cosmic neighbors in name only, destined for separate futures. Laniakea is not an isolated island. Its flowing borders touch other immense superclusters like the Perseus Pisces and the Shapley Supercluster, which itself lies beyond Laniakea's frontier. At these boundaries, the cosmic watershed divides, with galaxies making a gravitational choice about which deep well they will ultimately fall into. This dynamic picture turns our local universe into a living landscape of converging rivers. We are not merely in a cluster, we are of the flow. Our galaxy's journey is part of Laniakea's grand, slow-motion collapse toward its dense core, a process that will take many billions of years. This case study did more than give us a new name for home. It gave us a new way to see. It demonstrated that the cosmos is organized by motion, and that by listening to the current, we can finally hear the true shape of our immense heaven. This fundamental disagreement is known as the Hubble tension, and it is a crisis in cosmology. On one side, measurements from the very early universe, using the cosmic microwave background, give us one precise value for how fast the cosmos is expanding. On the other side, measurements from the nearby modern universe, using stars and supernova as distance markers, consistently give a higher value. The numbers stubbornly refuse to agree, suggesting a fundamental flaw in our understanding. Now, a fascinating clue is emerging from the study of cosmic flows. Could the very river we are riding be distorting our view? The idea is both simple and profound. Our local measurements of the expansion rate rely on what is called the cosmic distance ladder. We use nearby stars whose distances we know to calibrate the brightness of farther stars, and then use those to measure even more distant supernova. This technique builds a ladder of measurements that extends into our cosmic neighborhood. But what if our neighborhood is not typical? We have already considered the possibility that we might live in a vast cosmic void, an underdensity. If that is true, the local expansion rate inside this bubble would be faster than the true global average because there is less gravity to slow it down. From our vantage point inside this faster expanding region, everything outside the bubble would appear to be rushing away more quickly than it truly is on a universal scale. Our local measurement of the Hubble constant would be artificially high, neatly explaining the tension with the early universe value. The opposite could also be true. If we were in a region slightly denser than average, our local expansion would be slower, and we might be underestimating the true global rate. The key is that bulk flows are the direct evidence of such an imbalance. The coherent motion of thousands of galaxies toward or away from us is the fingerprint of a gravitational landscape that is not smooth. That landscape directly affects the local stretching of space. Researchers are now using our most detailed flow maps to model this effect. By reconstructing the full gravitational potential of our local universe from galaxy motions, they can estimate the true background expansion rate that would be measured by an observer in a perfectly average place. Early results are tantalizing. Some studies suggest that accounting for our motion through this lumpy cosmos could explain a significant portion, though likely not all, of the Hubble tension. This transforms cosmic flows from a fascinating curiosity into a critical diagnostic tool. They are no longer just about where we are going, but about calibrating the most basic ruler we use to measure the universe. If local flows are biasing our cosmic yardstick, then every new, deeper map of galactic motion brings us closer to a true measurement of the universe's expansion, and perhaps to resolving one of the greatest puzzles in modern science. Mapping the river of galaxies requires instruments of almost mythical scale. Enormous telescopes scan the sky from remote mountaintops, their construction a feat of global engineering. Supercomputers, consuming vast amounts of energy, run simulations that model billions of years in a day. The financial and environmental costs of this big science are undeniably real, raising a profound ethical question for our time. In a world confronting urgent challenges, how do we justify the immense resources poured into charting the motion of galaxies billions of light years away? The answer is not found in dismissing earthly concerns, but in understanding the deeper, often hidden, returns of fundamental exploration. The pursuit of pure knowledge has a long history of sparking unexpected revolutions. The drive to understand the heavens gave us the mathematics of calculus, the precision of optics, and the entire foundation of orbital mechanics that now enables global communication and weather forecasting. The technology developed to capture a single photon from a distant quasar refines the sensors in medical imaging machines. The algorithms created to find a hidden filament in a galaxy survey improve the software that manages complex power grids. This is the innovation dividend of curiosity. By pushing engineering to its absolute limits to answer a question about the cosmos, we inevitably create tools that filter down into society, solving problems we had not yet imagined. Beyond tangible technology, there is the incalculable value of inspiration. A single image from a deep space telescope or the story of a cosmic river can ignite a lifelong passion for science in a young mind. That spark is not a trivial thing. It is the seed of future doctors, engineers, climate researchers, and teachers. Investing in cosmic cartography is in part an investment in this pipeline of wonder, nurturing the next generation of problem solvers who will tackle the very earthly issues we worry about today. Yet, this justification carries a weight of responsibility. The scientific community must practice rigorous stewardship, minimizing the environmental footprint of its facilities through renewable energy and efficient computing. It must communicate its work with clarity and humility, making a compelling case for how the quest to understand our place in the universe ultimately enriches human culture and expands our collective imagination. This research addresses a question as old as consciousness itself: where do we come from, and what is the nature of the reality we inhabit? Providing even a piece of that answer is a profound human achievement, a legacy that reminds us we are capable of more than conflict and consumption. We are a species that looks up, that maps the invisible currents of the cosmos, and in doing so, we learn not just about the universe, but about the boundless potential of the curious mind within it. The raw data of galactic motion is not confined to supercomputers. It spills from the screens of scientists and into the studios of artists, where velocity fields become swirling pigments and gravitational potentials shape resonant soundscapes. This creative translation is far more than decoration. It is a parallel form of inquiry, using emotion and intuition to explore truths that numbers alone can struggle to convey. One artist might take a data set from the Sloan Digital Sky Survey, a table of coordinates and velocities for 10,000 galaxies. In their hands, each galaxy becomes not a point, but a stroke of paint. The direction of its motion dictates the brushstroke's angle. Its speed determines the stroke's length and color intensity, with faster galaxies burning in hot yellows and reds, slower ones drifting in cool blues. The resulting canvas is a vortex of color and direction, a direct visual echo of the coherent flows we have mapped. You do not need to understand redshift to feel the pull of the composition, to sense the powerful current guiding every element toward a common focal point. This offers an immediate, visceral understanding of bulk flow that bypasses the intellect and speaks directly to our innate sense of pattern and movement. Other creators work in 3 dimensions, crafting immersive installations. Imagine walking into a dark room where thousands of delicate glass filaments hang from the ceiling, each one representing a dark matter thread of the cosmic web. Embedded within this sculpture are points of light, galaxies, that pulse with a soft glow. Their pulsing is not random, it is a slow, rhythmic code. The frequency of the light corresponds to that galaxy's peculiar velocity, its unique motion within the grand flow. As you walk through this forest of light and glass, you are literally inside a data sculpture of the local universe. Your body navigates the voids and filaments, and your senses absorb the synchronized rhythms of moving galaxies. This transforms an abstract concept into a physical, navigable space, making the scale and structure of the cosmos something you can move around and through, fostering a profound, embodied sense of connection. Perhaps the most abstract yet deeply moving interpretations are sonic. Composers and data sonification specialists assign musical notes to parameters of motion. A galaxy's distance from Earth might set its pitch, while its velocity dictates its volume or the instrument that plays it. When the data for a massive supercluster is fed through this algorithm, the result is not noise, but a deep, resonant chord that emerges from the chaos, a harmonic convergence of countless points. The repulsive push of a cosmic void might translate into a spreading, dissipating silence, a hole in the musical texture. Listening to such a piece, you experience the universe's structure through time, hearing the great flows as themes and variations, the voids as rests, and the eventual merging of clusters as a crescendo of harmony. This auditory map allows us to perceive correlations and patterns that might be missed by the eye, as our brains are exquisitely tuned to detect rhythm and melody within complexity. These artistic endeavors do more than translate science, they complete a vital feedback loop. By presenting data in a new sensory language, they often reveal subtle patterns or asymmetries that the original researchers might have overlooked. The artist's choice to emphasize a certain flow through color or sound can prompt a scientist to re-examine that region of the data with fresh curiosity. Furthermore, this work builds an essential bridge. For many, the equations of cosmology feel like an insurmountable wall, a painting that swirls with galactic purpose, or a sculpture that pulses with the rhythm of the cosmos, offers a door through that wall. It creates an emotional entry point, a sense of awe and wonder that can then fuel the desire for deeper understanding. The art says, this is not just data, this is a story, and you are part of it. In giving us new eyes and ears for the universe, these artists remind us that the journey to comprehend the cosmic river is not merely analytical. It is a fundamentally human act of seeking beauty and meaning in the grand tapestry of motion. The beauty of our cosmic maps depends entirely on the sharpness of their lines. Every velocity measurement, every arrow pointing a galaxy's way, carries a hidden margin of error, a tiny blur that, when multiplied across thousands of galaxies, can distort the river's true course. The quest now is for precision cosmology, a meticulous effort to eliminate these blurs and turn our intriguing sketches into high-fidelity blueprints of gravity's hidden terrain. This work is less about grand discoveries and more about quiet, relentless refinement, examining every assumption in our measurement chain. The first and most fundamental challenge is calibrating the redshift itself. A galaxy's redshift is not a single, clean number. It is a signal that must be extracted from starlight, and that light has traveled through a minefield of distortions. Our own galaxy's interstellar dust dims and reddens the light of distant galaxies in a process called extinction, mimicking a subtle, false component of cosmological redshift. Astronomers must painstakingly model this dust, using maps of our Milky Way's own structure to subtract its contaminating effect, ensuring the redshift we measure is truly from the expansion of space and the galaxy's own motion, not from our own cosmic backyard. Then there is the light within the distant galaxy itself. The spectrum we analyze comes not from a single star, but from a blend of millions, each with its own motion within the galaxy. This internal churn broadens the spectral lines, adding a fuzzy uncertainty to the precise measurement of the galaxy's bulk velocity. Scientists are developing ever more sophisticated templates, models of stellar populations, to account for this internal blur and pinpoint the galaxy's true center of mass motion. But perhaps the most profound source of potential error lies in the step that converts redshift into distance. Our primary method uses the galaxy's apparent brightness. The assumption is simple: a galaxy of a known intrinsic brightness will appear fainter the farther away it is. But what is its true, intrinsic brightness? This depends critically on the galaxy's type, its age, its star formation history, factors governed by complex models of galaxy formation. If our models are wrong, our distance estimates are wrong, and the derived peculiar velocity becomes a flawed data point in the flow map. This drives a symbiotic relationship between cosmology and astrophysics. As cosmologists demand more precise distances to map flows, they pressure astrophysicists to refine their understanding of how galaxies evolve and shine. New surveys are identifying better standard candles, like specific types of supernova or the rhythmic pulsations of certain stars, to build a more reliable cosmic distance ladder independent of galaxy models. The frontier, however, is in extracting velocity information without needing a full, time-consuming spectrum at all. This is the promise of photometric surveys, which measure galaxy brightness through a few broad color filters. From this limited data, astronomers can estimate a photometric redshift, but it is far less precise. The breakthrough lies in developing new statistical estimators, clever mathematical tools that can infer the likely peculiar velocity of a whole population of galaxies from their photometric data alone, by looking at subtle distortions in their clustering patterns. These methodological refinements may seem technical, but their goal is profoundly simple: to cleanse our view. Each corrected error, each better calibrated instrument, removes a layer of fog from the window. We are polishing the lens through which we observe the cosmic river, striving for a moment when the current's every eddy and ripple comes into perfect, unambiguous focus. Only then can we be sure the dragons on the map are real, and not merely ghosts in the data. This global map is woven together by a symphony of instruments scattered across the planet and beyond our atmosphere. No single observatory, no matter how powerful, can capture the entire cosmic river in its full depth and clarity. The night sky is divided between hemispheres, and different wavelengths of light reveal different chapters of the story. To create a seamless, all-sky portrait of galactic motion, scientists have forged alliances that transcend borders, uniting telescopes and minds in a shared pursuit of a unified cosmic atlas. This is the era of global collaboration in cosmology, where the quest to understand our place in the universe has become a catalyst for profound human cooperation. Consider the Dark Energy Spectroscopic Instrument, a monumental project that is not the work of one nation, but of a worldwide consortium. Mounted on a telescope in Arizona, DES's robotic array can simultaneously measure the light from 5,000 galaxies, quasars, and stars. Yet its power is multiplied by the data it incorporates from a constellation of other facilities. Its target list is informed by deep imaging surveys from the Subaru telescope in Hawaii and the European Space Agency's Gaia Observatory in space, which provides exquisitely precise positions for billions of stars. To fill in the southern sky, it relies on observations from the Victor M. Blanco telescope in Chile. This is not a solo performance, but a meticulously coordinated orchestra, with each instrument playing its essential part to compile a three-dimensional map of unprecedented scale and detail. The collaboration extends far beyond optical light. To peer through the dense dust clouds of our own galaxy that obscure the Great Attractor, astronomers turn to radio telescopes like the Parkes Observatory in Australia and the Green Bank Telescope in the United States. Their observations of hydrogen gas reveal galaxies hidden from optical view, charting the hidden contours of our local gravitational basin. Meanwhile, arrays like the Very Large Array in New Mexico and the Future Square Kilometre Array, spanning South Africa and Australia, map the universe in radio waves, providing independent velocity measurements that cross-check and refine the optical data. Space-based observatories, free from the blurring effect of Earth's atmosphere, add another critical layer. The Hubble Space Telescope, a project of NASA and the European Space Agency, provides the sharp, deep images needed to measure the fine details of galaxy shapes and distances, anchoring the cosmic distance ladder. This logistical tapestry is mirrored by a human one. A single major survey like DESI or the Sloan Digital Sky Survey involves hundreds of scientists from dozens of countries. Early career researchers from institutions in Europe, Asia, Africa, and the Americas work side by side, virtually and in person, to calibrate instruments, process petabytes of data, and interpret the resulting maps. Weekly video conferences connect teams across time zones, where a question posed in French might be answered in English, with follow-up analysis coded in Python by a colleague in Japan. The shared goal erases traditional boundaries, creating a unique scientific culture where the only currency is curiosity, and the only loyalty is to the data. This planetary effort illustrates a beautiful truth about our species. When confronted with a question of cosmic significance, we instinctively pool our resources, share our knowledge, and link our technologies. The drive to map the invisible currents of the universe has become a quiet, powerful engine for diplomacy and shared purpose. In an age often defined by division, these collaborations stand as a testament to what humanity can achieve when we look upward together, aligning our collective gaze toward a common horizon of understanding. The resulting map is more than a chart of galactic flows. It is a mirror reflecting our capacity for unified exploration, proving that the river of galaxies is charted by a river of human connection, flowing just as strong here on Earth. This grand synthesis of data, theory, and collaboration points toward a single, magnificent destination. The ultimate goal is not merely a static atlas, but a living, breathing simulation of our cosmic neighborhood, a complete dynamic model that acts as a digital twin of the local universe. Imagine opening a portal on your screen, but instead of a game, you are greeted by a perfect, physics-driven replica of everything within a billion light-years. This is not a simple three-dimensional map of where galaxies are today. It is a fourth-dimensional model, a cosmic clockwork that you can wind backward to witness the great clusters assembling from primordial gas, or forward to watch the relentless flow of galaxies toward their gravitational destinies. Every known and inferred parcel of mass, from the brightest star to the most diffuse dark matter filament, would be accounted for, their gravitational interactions calculated with exquisite precision. The model's core purpose would be to test our understanding to its breaking point. A cosmologist could propose a new property for dark energy or a slight tweak to the law of gravity on vast scales. Instead of waiting decades for new telescope data, they would input this new physics into the digital twin and press play. They would watch as the simulation recalculates 14 billion years of cosmic evolution in a matter of hours. Then they would compare the resulting flow of galaxies, the shapes of the filaments, the distribution of clusters, to our real-world observations. Does the simulated universe develop a bulk flow that matches the one we see racing toward Shapley? Do the peculiar velocities of galaxies in the voids align with the data? Any mismatch is a glaring clue, a signpost pointing directly toward a flaw or a breakthrough in our fundamental theories. This model would also become the ultimate predictive tool for observers. Planning a massive new survey to study a specific filament, the digital twin could identify the most promising patches of sky, predicting exactly which galaxies will be flowing the fastest and where to find the faintest traces of intergalactic gas. It would tell us where to point our telescopes to find the hidden giants whose gravity we feel but whose light we have not yet captured. For educators and the public, this dynamic model offers something even more profound, a chance to explore. You could choose a single galaxy, perhaps our own Milky Way, and follow its trajectory across cosmic time. You would see it born from a collapsing cloud of gas, watch it merge with smaller neighbors, and trace its long, spiraling fall into the Laniakea supercluster. You could zoom out to witness the great rivers of galaxies converging, or zoom in to see how the local flow influences the very gas clouds where new stars are born. This transforms abstract data into an intuitive, visceral experience of cosmic interconnectedness. The creation of such a model represents the final stage of the scientific process for this grand endeavor. We began by collecting raw data points of light with redshifts. We learned to translate that data into maps of motion, revealing the hidden rivers. We used those motions to infer the unseen landscape of mass. Now we would integrate it all into a single, self-consistent engine of understanding. The digital twin is the point where observation, theory, and simulation converge into a unified story. It is the culmination of centuries of cosmic cartography, a tool that does not just describe the universe, but allows us to hold a working copy of it in our hands, to ask it questions, and to listen with newfound clarity for its answers. The universe is not a silent, static museum. It is a symphony of motion, and for the first time we are learning to hear its rhythm. Our journey through the hidden cosmic flows has revealed a cosmos far more dynamic and interconnected than the simple image of an expanding balloon. We have traced the great rivers of galaxies, from the obscured pull of the Great Attractor to the staggering gravitational dominion of the Shapley Supercluster. We have felt the repulsive push of cosmic voids and confronted the tantalizing, controversial whispers of dark flow from beyond the horizon. Mapping the motion of thousands of galaxies has unveiled a universe in a state of graceful, gravitational choreography, its grand design sculpted equally by the brilliant metropolises of clusters and the profound, active emptiness of the voids. These flows are far more than astronomical curiosities. They have become essential diagnostics, a new language for probing the universe's deepest secrets. The coherent streams of galaxies are a direct readout of dark matter's invisible architecture, proving its tangible presence in the sloping terrain of spacetime. The slowing growth of these flows over cosmic time carries the fingerprint of dark energy's accelerating push. Even the subtle tensions in our maps, the Dipole Discrepancy, the scale of the largest currents, serve as stress tests for our fundamental laws. questioning whether Einstein's gravity holds perfectly on the largest scales or if new physics awaits discovery in the deep currents. This story is accelerating as next-generation telescopes like the Vera Rubin Observatory and the Euclid space mission come online. Our maps will transform from detailed sketches into ultra-high-definition films of cosmic evolution. These new eyes on the sky promise to resolve our current mysteries. They will deliver a verdict on dark flow, precisely measure the universe's potential lopsidedness, and finally tell us if we truly reside in a vast cosmic void. Yet with greater clarity comes greater wonder. Each answered question will undoubtedly unveil new, deeper mysteries we cannot yet conceive. So remember this. You are not a stationary observer. With every breath, you are a passenger on this grand cosmic current, riding a galaxy that sails a river older than our planet. This shared journey connects us to every star in our local stream and to the immense hidden landscape that guides us all. If this exploration of the universe's secret rhythms has captivated you, we would love to hear your thoughts. Share what amazed you most in the comments below. Subscribe for more journeys into the heart of space mysteries, and always keep looking up. The map is never finished, and the universe, as we now know, is always in motion.